This question asks us to consider what are the significant resonance contributors. And now this is where the art of organic chemistry really comes in at, because a significant resonance contributor is somewhat subjective. And so you have to be able to use all of your chemical knowledge to decide, is a structure significant or not? And we have some general rules. If we're going to have a positive charge, we want it to be on the less electronegative atom. If we have a negative charge, we want it to be on the most electronegative atom. We can't ever form more than one. We can't ever form more than 4 bonds, right? So we can't break the octet rule by having more than 4 bonds. But other than that, it's very much sort of an examination and an application of those rules. Now, what I've done is I've drawn the frameworks here of all the different molecules, and we're going to take a look and see what we can figure out for resonance contributors. Now, let's think about this. Can I show the electrons in the pi bond moving to that carbon so that I end up with a lone pair there and a negative charge on the carbon and everything else being the same? Certainly. But is that the most important contributor? No, it isn't. So what I want to do in order to figure out the most important contributor is think about how far electrons can be delocalized, how far a resonance structure can take the electrons. The longer distance that they can be delocalized, the more important that contributor is, because the more stable it is. What I can't show is I can show these electrons moving up to here. But in order to do that, I'd have to do something here because it's already got 4 bonds. So if I make a double bond there, then I have to move electrons here onto the nitrogen. And now I can do that because instead of having the negative charge on the carbon like we were showing before, the negative charge is now on the nitrogen, and that's more electronegative. So this is the most important resonance contributor out of the two that the two that we thought about. Okay, let's think about this one. All right, what's this going on with this positive charge here? That positive charge on the carbon means that this carbon is got an incomplete octet. So that means that we can move double bonds towards it. So I can move the double bonds over here. If I do that, then what that does is that makes this carbon positive. Now, there's still room to move double bonds in the molecule because I have a pi bond right next to it. So that means I can make the pi bond here. Now, if I did that, the positive charge would be there. But let's take another look. I still have a pi bond adjacent to it. So I can move that pi bond to this location. And instead of having a positive charge there, I can have a double bond there. Now, what else? If I do that, that means that the positive charge is there. Now, the positive charge is delocalized. It's on a carbon, but I can continue to go further by showing a set of electrons from the oxygen moving down and making a pi bond with the carbon so that I end up with a double bond on the oxygen. And what that does is it makes the oxygen positive. So which one is the most important resonance contributor? Well, in this case, we're going to go ahead and let the positive charge be on the oxygen rather than on the carbon, because generally the longer delocalization beats the rule of having the positive charge be on the less electronegative atom. Oxygen versus carbon, in this case, you'd want to say carbon, but we're going to go ahead and let the electrons delocalize more and get all the way over there from the oxygen. So we look at it from the perspective of kind of filling in the hole of the positive charge. It is much, I think it's much better to think about it in the perspective of where the electrons came from, not where they moved to. So we would say the electrons from the oxygen would move the pi bond, come make a pi bond in between those two carbons, which would move that pi bond to there, which would move that pi bond to there, which would move that pi bond to there. And I think either way you get the same result as far as bonds, but the last way to think about it is probably a little bit more accurate and a little bit more helpful when it comes to thinking about reactions later on down the line. Okay, so let's take a look at the next one. I still got a framework worked out. And so let's think about what can happen. Okay, can I move some electrons here and then move this over there? Well, if I did that, what would end up being the situation? Well, I would end up with 1, 2, 3, 4, 5, 6 electrons there. That would be a negative charge on an oxygen. But what about this oxygen? This oxygen was already positively charged, and I've now moved electrons away from it. So it would go from having a +1 positive charge to having a +2 positive charge. So that's not at all an important resonance contributor. What we're going to say is the more important resonance contributor in this case, and is really the only correct answer, I think, for this particular question, is we're going to allow this double bond to stay exactly where it is so that that oxygen remains neutral. We're going to let that lone pair on that oxygen come up to that oxygen to make the oxygen neutral. And then we're going to let the positive charge live on the carbon. I think that's the most important resonance contributor. Okay, what about this last structure? Let's take a look here. That carbon has a hydrogen and a negative charge, so that must be a lone pair of electrons there. And so let's think about which way it can go. Can I move the electrons here? Well, the answer is yes, only if I do something about these electrons. Well, what could I do? Can I continue to move the electrons around the circle? Well, if I did that, what would happen? I'm only going to draw this top part of it. I've got a carbon with a hydrogen. We already made a double bond here. If we continue to show those electrons moving around here, that's what we would end up with. And that's wrong, right? Because that carbon has 5 bonds. So we can't let that set of electrons move all the way around the circle. And in fact, the limitation is that I can show resonance to that location only. And so what that would do is it would put a double bond here, and it would make the negative charge delocalized to that side. Now, this is a symmetrical molecule, so I could have shown it in this direction as well. But remember that if I just take this and I rotate it around the axis, I get the same structure. So there really aren't 2 possibilities. There's only 1 possibility, and I can show a difference. I can rotate it so that it kind of looks the same. Remember that line structures have some limitations, and one of the limitations is it's easy to, when you're dealing with a symmetrical molecule, to think there's more than 1 option, but that symmetry means that really there's only 1 option. Okay, that's it for this question. Thanks.